And then we can have a look at some questions that a student sent me via email. And the first question is related to task 14. I don't know how to solve this problem, but I found this formula on ChatGPT. I don't know if there's a ChatGPT 5 version already available. I don't know what this means, but I don't know the derivation of this formula and if it's enough to write this only in the answer. Okay, so we can check task 14. Yeah, that's a good point. I mean, maybe we can think about this problem and then okay, and now okay, it's not ChatGPT 5. The result that ChatGPT gave at the end is 5R divided by 6. That's the result. Okay, so now I understand this answer here. So yeah, this is something that we could definitely also check. So I will copy this here and paste it into my drawing program by opening a new page after the stuff that we already discussed. And what we can try to do here is to redraw the circuit. That's the idea of this task, to calculate the equivalent resistance of this resistor cube, let's say. And the question is, if we have a current flowing towards this node and then flowing through all the resistors here in a certain way, of course, and exiting this node, what would be the equivalent resistance of this resistor cube between the two corner points 1 and 7. And there is a node, and this node is very useful. We should use symmetry and equality of potentials in the circuit. And yeah, if you know how to do it, it's kind of simple. If you don't know how to do it, it can be very tricky. But yeah, let's try to do something like this, that let's say on this side, so the problem here is that it's very difficult to see which resistors are in series or in parallel to each other because of this three-dimensional geometry, and some currents will go up and some currents will go to this side and to this side and so on. So the idea is we will redraw this circuit, this three-dimensional circuit. Of course, it's a two-dimensional projection of the three-dimensional circuit into a two-dimensional circuit, and that all the resistors, let's say, are horizontal, point in this direction, and only current is flowing into one direction. So we start here, this is node 1, and we end up here on the other side, this is node 7. And so now if we check from node 1, we have three options. We can go to node 5 over 1 resistor, to 4 over 1 resistor, and to 2 over 1 resistor. So what I can do here is I can try to make a branch and say, okay, we have three choices. We can go with 1 resistor. I will once again use the German European symbols. Over 1 resistor, then we are at node 5. We can go over another resistor. Then we are at node 4. And we can go over a last resistor from this node. And now we go to node 2 in the circuit, or in this cube, or the edge 2. Okay, so now we are somehow here, here, and there. And so if we look, okay, from node, or from each of these edges, corners, we have 2 more choices. So from 5, we could go to 8 and to 6. From node 2, we can also go to 6 and to 3, and from 4 we can go to 3 and to 8. So from 5 and 4 we can go to 8. So I should draw the 8 maybe somewhere here. So here we can go to, this should be 8. So from the 5, I will draw this a little bit slanted. From 5 we can go to 8. And from 4 we can also go to 8. It's not really looking super nice. I will, why is this so small? I will redraw this here. So from 4 and 5 we go to node number 8. And from 4 and 2, in both cases we go to node number 3. So some slanted resistor in this direction, some slanted resistor going upwards here, and in both cases we end up at a joint node number 3. Yeah, and here it's a bit challenging. So from 5 we go to 8. No, from 5 we go to 6, but from 2 we also go to 6. So from 5 we go up to node number 6. And now yeah, I will do it very unconventional and say also from 2 we go to 6. And this connection I will draw here the other way around to do not have some overcrossing, but this is the same 6 here. And so from the 6, the 3 and the 8 over another resistor we always go back to 7. So from here I have a resistor going to 7, from here I have a resistor that goes to 7, and also from the 6, maybe I will use the 6 here at the top. Cannot change the 6, so this is the node 6, and also from 6 over some resistor we go to the 7, and this all goes together to one node going to 7. Okay, and all these resistors are equal. And so because all these resistors are equal, and because of this kind of symmetry that we have, that okay, we start here, we go to 3 resistors, and from each of the 3 resistors via 2 other resistors we go to 2 other nodes, and from there we always go with another equal resistor to the last node. There should be no difference between this point, and this point because of the symmetry of the circuit. So if I use this symmetry and potential equality, I can connect these points with each other, because there should be no difference between these 3 points. So this should be the same, this should be the same, this should be the same. And in the same way I can also connect these 3 points with each other. I mean, this is already connected via here. because there should be no difference between these 2 points or these 3 points. And so now if we check now, because of this virtual connection here that is allowed due to symmetry and this equality of potential, these 3 resistors are connected in parallel. So we have from this some equivalent resistance of 3 resistors in parallel. So if we call this R here, the 1 kilo ohm, then it's R divided by 3, because we have 3 in parallel. Then here we have 1, 2, 3, 4, 5, 6 in parallel. So we have R divided by 6, and at the end we have another R divided by 3. So the total resistance R divided by 3. So the total resistance is, so this is 2 over 6, this is another 2 over 6, so it's 5 over 6. So the total resistance, as already mentioned, if we combine this into one equivalent resistor at the end, then it's 5R divided by 6. So the ChatGPT answer in this case is right, and the derivation would be to redraw the circuit and to make use of this node here and use the symmetry and potential equality in this circuit.